Every challenge question, part 29, it's the numerical methods chapter. So we've got some Newton-Raphson to do here. This is the formula. So of course we need to differentiate this. A fifth goes away. This is product rule here, so we differentiate x just to 1 and then keep this the same. And then we leave this alone and then differentiate this for minus 2x into this thing. Times by this x makes minus 2x squared. Now if you set that to equal 0 and solve, you can factorize out the e to the minus x squared, which is of course never 0. And therefore to find stationary points, this would have to be 0, which gives you x is plus or minus 1 over root 2. So therefore, this stationary point here is at 1 over root 2, which is cool because you can just see beyond that, this is always a negative gradient because it's coming down here and then it's asymptoting down to a fifth. Now, if you know how Newton-Raphson works, you'll know that what you do is you pick an initial point, you go up to the curve, you draw a tangent to the curve, and then wherever that tangent hits the x-axis, you go up to hit your curve again, then you draw a tangent, then you go up, hit the curve again, draw a tangent, and you just do that until you get to a root. Except, of course, if this gradient is always negative, the tangents are always going to be pointing in this direction, and therefore you're never going to make any progress and get towards here. So okay, we can just say f dash of x is always negative when you put in something bigger than 1 over root 2, because of course this is always positive, and so of course, and this becomes negative, positive times negative is negative. So that's fine. And formally, we can now say, well, f of x itself is always positive, because of course you've got the asymptote at 1/5. It's positive here, so it's always going to be above the axis here. And so Newton-Raphson is going to take a number and then take away a positive divided by a negative. A positive divided by a negative is a negative, so taking away a negative is a positive, and you just end up adding stuff in to wherever you started. So yeah, we're going to start somewhere, and then we're just going to get bigger and bigger and bigger, as the graph suggested. So that'll be the proof. Taking minus 0.5 as your starting point, though, use Newton-Raphson to find a root. So we can do that. Just put in minus 0.5 in here. I typed it like this. And the reason I typed it like this is because it meant that I could press equals. I don't care what the answer is, because then I could just go in and edit all of these for ands, and you get this. And you can just type it. You just spam the equals button until the first 3 digits don't change anymore, and you get this. It's fine. Just do it. Cool. Next question is about the other sort of numerical method, which is the GCSE style iteration that you will have seen there. So of course we're doing f dash of x equals 0. So the obvious thing to do is differentiate this twice. So I've done that, set it to 0. You can just divide everything by 2. And then it wants us to rearrange this, this, and this. So the first one, just isolate the 3x and then divide by 3. The second one is a little bit more complicated. You take away the 7, or move the 7 over here, then factorize out an x and then divide by what's left, which is this. And the third one, you isolate the 15x to the 4, divide by 15, and then 4th root. And we get our 3 things. That's all very easily. Now, choosing a suitable formula, find the one that finds the b. Now, basically, these x4 and x3 powers mean that these ones aren't going to work very well, because the thing just gets really big really quickly, and you don't really get anything. Except that's not quite true. Because, of course, this one is dividing by that thing, so it seems like this one has some hope. This is the obvious one to try, and, of course, this is the one that ends up working. I did think, just because it will be more interesting, I would show you what some of these look like. So if you don't know how iteration works, what you do is you change the focus of the question from asking when, this graph, or sorry, this one here, change it from when this equals 0, you change that question to when this graph here equals x. So in other words, instead of asking when the original thing is on the axis, the y equals 0 line, you instead change it to when does this graph here meet the line y equals x. And that's how iteration works. So you can see here, this is an example of a graph that we don't have, but this is iteration working, right? You have the line y equals x, and you ask when does that equal whatever other curve you're looking at. And what iteration does is you pick a starting point, you go up to the curve, in this case like 0.19, and then you go to the y equals x line, because that will essentially, if you go across to it, give you the new input of 0.19. So you've got an old input of 0.1, you find a new input, or output, I guess, first of 0.19, which changes to your new input, and then you just repeat the thing again, because you just spam the equals button, right? So with 0.19, you find the new output, which is like 0.3, so 0.3 becomes the new input, which you put in to get 0.4, that becomes the new thing, and you gradually get towards the thing. And you snake, or cobweb, towards, or staircase towards the solution here. Now that's how it's supposed to work. Unfortunately, if you look at the first graph we got given, this is what happens. So we start with 0.5, I guess. I'll zoom in a little bit. You start with about 0.5, you go up to the curve, and immediately you're at like 2, which then you have to go to the input, new input 2, and then find where that hits the curve, which is like minus a lot. It's like minus 81. And then, of course, you go to minus 81 as your new input and try and find the curve, which is like minus a lot. And then very quickly it spirals out of control. If I zoom out, you can see it's just gonna spiral out of control very quickly. I'm not even sure I can find the next input very quickly. There it is. And then it goes down to another input, which is a long way down. So this just doesn't work. And again, it's because of that x to the power 4 thing that's going on. That just means that doesn't work very well. The second one does something quite interesting here. The second one, with an input A, you go up, you find your new input, which goes to here. You find there, which gives you a new input of, well, that was like a 0.4, so that would be a new input of here, which takes you to there. And you end up going around in a box like this, and you end up getting trapped in a box between 0 and like 2.3 or something like this. And it doesn't really matter where you start. This is kind of interesting. You just get trapped in this box. Even if you go all the way out here, you still get trapped in the box, or over here, you still somehow manage to get trapped into this box. I think it's because of this inflection point here that's causing this to happen. Although I guess if the inflection point weren't there, it would just spiral out of control, like the previous one did, and get bigger and bigger and bigger. So either way, it's not getting our solution. We're not narrowing onto this point here. So that's not good. The last one, however, as we discussed, the last one works, and the last one works wildly efficiently. You can see it zooms right into the solution very, very quickly. It cobwebs towards there extremely fast. So yeah, we put in an input and we move around, and you can see it just zeroes in on that solution almost immediately. It doesn't matter whether you're to the left of it or to the right of it, it zeroes straight in there. We can zoom in again and see, but it's going there very, very fast. A good 3 iterations get you towards 3 decimal places. That's very fast indeed. So that's going to be the one that we're going to pick, and that's going to be the one that works. It gets us, as we saw in that picture there, to about 0.750. Now, explain why we can't use the same formula, which is this one here, to find the coordinate of A. Well, as you saw in the picture there, if I zoom back out again, because this graph, the 4th power graph, doesn't exist below the x-axis, because we're not doing plus minus the 4th power, or the 4th root, we're just doing the 4th root. There is no intersection with the y equals x line down here. So therefore, of course, we can't find this thing over here because there's no corresponding solution in this situation here. If we drew the graph both ways, we could maybe find it, but that's not what we're doing. We're not doing plus or minus, we're just doing the plus. So that's not going to work. And finally, it asks us to find Newton-Raphson to find an estimate of A this time, because we couldn't do it any other way. So we differentiate again, and then we can use the formula. I just chose -1 to start with. I put it into here, and I put it into here. Like this, I got this, and then I set up the same sort of thing I did last time, spammed the equals button, and eventually you get to this number, which doesn't really change. And you have your answer. Thank you so much for watching. I'll see you next time.